So what is volume by cross-section? Essentially, what is presented to you is that an object has a base of a given area. For example, the base can be this given blue circle. The base of the object can be this shaded green region bounded by the function of square root of x and x squared. Or the base of the object can also be this green shaded region bounded by these two functions of y. For this example, we will be using the blue figure on the left. So a possible object with the given base of the blue figure on the left can be this object in the middle. Then to calculate the volume of that object, you do this by taking cross-sections of the object in a given shape. In other words, you're slicing that figure an infinite number of times, slicing each slice infinitely thin. The shape of the slice can be a 2D geometric shape, a square, rectangle, semicircle, or a triangle. So for this example, we will take the object and calculate the volume using cross-section of equilateral triangle. So we will slicing this object infinitely amount of times, and we'll be slicing each cross-sections in the shape of an equilateral triangle. So if we do that, the resulting image will look something like this.
As you will notice, each cross-section of the triangle is not the same size, because the distance across changes throughout the base. Therefore, the distance across the region, for example x, is constantly changing. This means that the distance across in that region can be expressed as a function s of x. Therefore, the area of the cross-sections must be expressed as a function a of x. The volume of the object is thus calculated by adding the areas of each cross-section. Therefore, the equation of the volume of the object generated by the cross-section is v equals the integral from a to b of a of x dx when cross-sections are perpendicular to the x-axis, and v equals the integral from c to d of a of y dy in terms of y, so when cross-sections are perpendicular to the y-axis.
To find volume of a figure using cross-section of squares with side lengths of x, where these are the side lengths, and the side lengths can also be expressed as a function of s of x. So, as you know, the area of a square is the side length times the side length squared. So, given that, your area function is then a of x equals s of x times s of x, or s of x squared.
So we're going to go over finding the volume of a figure using cross-sections of equilateral triangles with side lengths of x. The function for side lengths can also be expressed as s of x. So since each side is s of x, this highlighted purple section is 1/2 of s of x. Using trig property, since this highlighted purple section is 1/2 of s of x, this means that the height of the triangle, or this gray line, is the square root of 3 divided by 2 of s of x. So given the side length, or also the base s of x, and given the height square root of 3 divided by 2 of s of x, you can plug this information into the formula for area of a triangle to derive the formula for the function of a of x, which is area, which is 1/2 s of x times the square root of 3 divided by 2 of s of x. Now we will find the volume of a figure using cross-sections of an isosceles right triangle with the leg of x. Using the definition of an isosceles right triangle, we can therefore say that this side and this side are equal, and they are s of x. We can say the hypotenuse is s of the square root of 2. To find the area of a triangle, we would say 1/2 the base times the height. Then, to find the volume, we would say s of x squared divided by 2 dx. Now we'll be solving for a semicircle with a diameter of x. So we know that a typical circle has a diameter, which is right here. We know the diameter has a radius, which is 1/2 the diameter. So we will therefore call the diameter s of x. In a typical area of a circle, we would say pi r squared, which is pi times radius times radius. Now when we look at the area of a semicircle, we're going to say pi r squared again. However, since it's a semicircle, we're going to say 1/2, because it is half the circle. So our new radius will be s of x divided by 2. Therefore, our area will be 1/2 pi s of x squared.
Okay, so this is a calculator AP question that uses a volume by cross-section. First, it tells us to only look at the first and second quadrants, and then it gives us the two equations we should use. Y equals 20 over 1 plus x squared, and y equals 2. So what it is actually asking us to do is a cross-section perpendicular to the x-axis using semicircles. The best thing to do first is to graph the equations and then immediately find the points of intersection. So that would look like this. Then once you plug it into your calculator, you can find the point of intersections, which for this equation would be here and here, and would be -3 and 3. And what we're trying to find the volume of is this section right here in between those two intersections. When doing a volume by cross-section problem that is perpendicular to x, you need your distance across your s of x to be the equation that is on top minus the equation that is on the bottom. So s of x here would equal 20 over 1 plus x squared minus 2. So it would be this equation first on top minus this equation on the bottom. Next, we have to write out the area, which is a of x, using the semicircle equation, which is pi over 8 times s of x squared. Now we're ready to set up the volume. So the volume, first you'd write down an integrand using the limits -3 and 3, which are the intersections. And basically what you do next is you take the a of x equation and just plug it in. So we write down pi over 8, and then we multiply that by s of x, which is 20 over 1 plus x squared minus 2, and then we square that portion. And then we write d of x. Once you write down this equation, all you have to do is plug it exactly into your calculator, and so that equals, your final answer would be 174.268. And that's how you do a volume by cross-section perpendicular to x using semicircles.
Find the volume of the solid whose base is the region bounded by y equals x squared, y equals 2, and the y-axis using cross-sections perpendicular to the y-axis. So first, I'm going to start off by graphing y equals x squared. Then I will graph y equals 2. And then as you can see here, it is the region bounded also by the y-axis. The base is the region of the shaded green section. The problem states that you're using cross-sections perpendicular to the y-axis, so instead of normally doing it in perpendicular to the x-axis, and you're doing it perpendicular to the y-axis. So therefore, you must solve y equals x squared in terms of x. So you have y equals x squared. To get rid of the squared of x and to isolate x, you take the square root of both sides. So then you would have x equals plus or minus square root of y. For this case, you can only have positive or negative, or you can only have one or the other. So since it's in quadrant 1 where all values are positive, x is equal to positive square root of y. However, another way you can test this is by plugging in a point on the graph and testing to see if it's plus or minus. So using the point 1, 1, I am plugging in x equals 1 equals plus or minus square root of 1. So the only way for 1 to equal square root of 1 is if it's positive. So therefore, x equals positive square root of y. So now we need to find what s of y is. So the base is the region bounded by these 3 lines. And to find the region bounded then that means s of y goes from x equals square root of y to the y-axis. So your s of y is the graph of square root of y across to the y-axis, so therefore it is square root of y minus 0, which is just square root of y. So now we need to find what a of y is. So the area of a square, as we defined before, is s of x times s of x. But in this case, because we're doing it in terms of y, since the cross-sections are perpendicular to the y-axis, we just use s of y times s of y. So therefore your a of y equals s of y times s of y, which then you plug in what you know have already defined for s of y, which is square root of y. So it's square root of y times square root of y. Now we need to find the limits of integration. So the region goes from y equals 0 to y equals 2 because we're doing this in terms of y. So c equals 0 and d equals 2. Your upper limit is d and your lower limit is c. Since we're doing it in terms of y, we do not go from x equals 0 to x equals 1. So the volume of the solid, using cross sections perpendicular to the y-axis, the formula for that we have defined is v equals the integral from c to d of ay dy. So plug in what we know, d equals 2 and c equals 0, and your a of y equals square root of y times square root of y. This is the equation we get for the volume of the solid. So to find this exact value, we take the antiderivative of y, which is 1/2 y squared, and then to find the exact value, we plug in 2 for y, subtract that and plug it 0 for y, and we get 2.
So in this problem, we will be showing cross-sections perpendicular to the x-axis with equilateral triangles. We have the equation x squared plus y squared equals 4. As you can see here, that's the triangle inside of the coordinates. It goes from -2 to 2. Therefore, we will put it in terms of y. So y squared equals 4 minus x squared, and we get y equals square root of 4 minus x squared. We would then say it would be positive because it would be in the first quadrant. Now, one side of the triangle would be 2 square root 4 minus x squared because we have two sides of the triangle to make up s of x. Now, to solve for the volume, we're going to use an integral, which ranges from -2 to +2. That shows the area underneath the curve. Now, in our volume equation, we're going to use the square root of 3 over 4, and you can see that from the previous video of showing what equilateral triangles look like, times 2 times the s of x, and you're going to square that s of x. Then you're going to use dx to show all the little cross sections to show that it is a volume equation. When you put in your calculator, you will get 18.475.